Happy Friday, Honors Math 2, and I am going to finish up the notes for 2.4 so that you guys can learn a little bit more about some special cases. And you can do area model for anything, but these are some cases that if you knew them and you recognize them, might make your life a little easier. So I need you guys to turn in the notes to this page. So we finished up on the block day here. We did this the last example, so turn the page and get to this page right here. Give you guys a couple minutes to do that. Okay, if I was here today, we would be separating this task into groups and we've been talking about it. But right now, I'm just going to kind of basically do everything. And it says factor each expression below if possible. Look at the similarities and differences among the expressions and the corresponding factored forms. Be prepared to share results with the class, then work with the class to sort them in groups based on the pattern. What makes these special? Well, I'm just going to skip all that and I'm going to kind of go through and talk about what could be special. First of all, I want you to look, there are some that are binomials. So, this one's a binomial, this one's a binomial, this one's a binomial, this one's a binomial, and this is a binomial. Okay? So, that's what's special about these. Okay? Now, one of them is not fitting the same pattern the other one. They all have an x squared. They all have some type of perfect square. 49 is 7 squared. 25 is 5 squared. 36 is 6 squared. 1 is 1 squared. And actually 9 is also 3 squared. And going back to this, 4 squared. 4 is 2 squared. Sorry, I don't know if I said that right. They all have something, they're all binomials. They all have a squared. This one doesn't fit the pattern of the rest. The reason, it doesn't have a squared. Or a difference. Sorry, doesn't have a subtraction. So, just to kind of talk about these. So let's say I was factoring f. If I was factoring f into an area model, this would be 4x squared. This would be negative 25. I would know that my cross product would be negative 100x squared because 4 times 25 is 100. But look at, there's no middle term. That's 0. We don't need 0 x's. The only way you can get 0 is to add a positive and negative. They're the exact same thing. So, if you can think about it, 10 and 10 make them 100. If we make one of them a negative 10 and one of them a positive 10, they'd give us 100. It also cancel out and give us 0, which we talked about a little bit. So if I'm doing this, this would be 2x, 2x. 2 goes into 10 5 times. 2x goes into negative 10, negative 5. And we get this problem, which we have multiplied out on the very first assignment. We've multiplied out. Okay? So we actually did an area model and multiplied that. You might want to just write that down. I'm not going to write everything down on here, but that works on there. Okay? So it's called a difference of two squares. Both parentheses are exactly the same except one's positive, one's negative. These other ones would be that, but this one's not. And let me just show you really quick why not. Because people think you can factor this. If I'm putting x squared and 4 here, I'm getting 4x squared, but I have to add up to be 0x. There's no way you can add two numbers and make 0 if they're both positive or both negative. This is actually not factorable. So I want you to at least write that part down. Okay? Everything else that I highlighted, not that one, so we're going to kind of cross that one out, is a difference of two squares. Okay? It follows into that pattern. I'm now going to highlight a few other ones, and I'm hoping you can see my yellow on my yellow. I'm going to highlight this one, this one, this one, and this one. And those have the same type of pattern, and they're a special one. And just to give you an idea, if I factor, well, let's go this one down here. So if I do j, 4x squared, 25, multiplying to be 100x squared, got to give me 20x. I picked that one because you might see it's 10 and 10 again. But now both of them are the same sign because everything has to be positive. So it'd be 10x, 10x, 2x, 2x plus 5 plus 5. So different than the last one, this one would be 2x plus 5, 2x plus 5, or we could write it as 2x plus 5 squared. Those are other special cases. Okay, I'm not, like I said, I'm not going to do all of them, but I'm going to give you some those special cases. Okay? Okay, turn the page. So we highlighted pink to be what's called difference of two squares, which will come in your notes in a second, and we highlighted these, which I'll talk about a little more, as perfect square trinomials. Okay? So just going to the next page, we may be able to recognize some that we might think are difference of two squares. I'm going to highlight in pink again. It's a binomial, two things, difference, subtraction, 5 squared, 1 squared. Difference of two squares, subtraction, 9 squared, 9 is 3 squared, 100 is 10 squared. Those are the other ones. This one, not factorable. So that one fits the pattern that I did before on the other page, which we'll do more notes in a little bit. I'm going to tell you that these two fit the pattern on the other one. And again, we'll go through it a little bit more, but they will come out to be perfect square trinomials. Both parentheses will be exactly the same. So it talks about down here, special quadratic expressions like 9x squared minus 100 in part f can be factored once you discover the pattern. But why do the patterns work? The quadratic expression u squared minus w squared is called a difference of two squares. I'm just going to highlight that. You can see the area model and recognize the pattern you might have found. Once you find the pattern, you don't have to do an area model. Okay? It will always come out to be the same thing. And it's going to come out where one parenthesis is going to be positive and one parenthesis is going to be negative every single time. Okay, so if I go back up here, you're going to see this problem come back later on. I don't want to multiply and get negative 900. That is crazy. Okay, but if you can recognize this is, 3x and 3x, one's negative 10 and one's positive 10, then you'll notice these are going to cancel out. So even if the numbers are huge, we can recognize one's positive, one negative, and we always get 0 in the middle. Difference of two squares in this format. Now, perfect square trinomials you may not recognize. Just to give you an idea, C is a perfect square trinomial. U squared plus 2uw plus w squared. The reason why, if I can take this and I can write it as x squared plus 2 times something times x, and I'm going to write this as 4 squared. So this is 4. So if you notice, I'm replacing w with 4. And you'll see the 4 squared is 16, and then if you double the 4, you get 8. Because when you do an area model for something like this, oops, sorry, this is x squared, my bad, this is 16, this is 4x and 4x, you are going to get the exact same thing twice, which is doubled. So this factors into x plus 4 squared. Called a perfect square trinomial. Not a big deal if you don't recognize that, but much easier if you recognize the difference of two squares. Okay, so I may not do all these examples. There's a lot. So we may kind of go through some fast things. Sometimes do area models, sometimes don't. But we are going to actually go to the next page in Factrum. So turn to the next page. This is the last page of homework, or notes. When you get to your homework, which is 2.4, 13 through the rest of it, those are all special cases. You can definitely use an area model for anything you want, but you don't have to. If you see the special case, don't use an area model. So for example, kind of tells you what the special cases go. If it's a squared minus b squared, and you guys, this doesn't have to be a squared. It could be the 4th power, 8th power, anything even. 1's plus, 1's minus. You basically take the square root of both those numbers, 1's plus, 1's minus. So x squared minus 64, x plus 8, x minus 8, because 8 squared is 64. 25x squared minus 36, you could square root both, 5x plus 6, 5x minus 6. So I am going to go down to this question right here. And I'm going to show you in an area model what this would be. I didn't write an area model there for this one, not sure why. 81x squared negative 1. Okay, I have to multiply to be negative 81, which is 1 negative 1 positive. And I have to add to be 0 because there's nothing in the middle there. We say the b term is 0. Well, you probably think of 9x and negative 9x. So 9x minus 1 plus 1. Basically, perfect square. Difference of two squares. The answer would be 9x minus 1, 9x plus 1. You can't write it any shorter than that because they're not the same. So if I recognize that, I don't have to do an area model every time. I recognize this is squared, this is squared. It has to be subtraction. I recognize that 10 squared is 100, so I could write like that. If I wanted to, I could check, or I can do an area model. But if I see the pattern, I see that those cancel out, and I give a negative 100. Same thing on this one, x minus 4, x plus 4. So it's nice to recognize patterns. Patterns always help you in math because they make things go a little faster. Okay, try this one real quick. 9x squared minus 400, because I wouldn't want to do that one. Big numbers, don't want to do it. But you guys can figure it out by recognizing the difference of two squares. Give you a couple seconds to do that. So if you're thinking about what we did before, we basically were taking the square root of 100, it's 10. The square root of 16 is 4. The square root of 81 is 9. The square root of 1 is 1. What is the square root of 9? 3. And you may or may not know what the square root of 100 is, but if you know the square root of 4 is 2, then the square root of 400 is 20. So I don't have to do a whole area model. I don't have to do the whole diamond problem. So I recognize that's a difference of two squares. I got squared things. I got a subtraction. Easy to do without an area model. Sometimes you'll look at a problem and be like, oh, that's a difference of two squares, like the next two examples, but there's nothing squared that's 12. You can't take the square root of 12. It's not a perfect square. Nothing squared is 48. But you may see a GCF. So if I'm looking at this, yes, there's 2 goes into both of them. Yes, 4 goes into both of them. Yes, 6 goes into them. But 12 goes into both of them is the largest GCF. You might not have recognized that. Now that looks as a difference of two squares. The square root of 4 is 2. So we could write this as x minus 2, x plus 2. Does not matter the order that you put the parentheses, but you do have to have the 12 in front of there. Okay, if I look at the next one, no, 27 is not a perfect square, either is 12, but I look for a GCF. I notice 3 goes into both of them. And then I notice that's a difference of 2 squares. Square root of 9x squared is 3x. The square root of 4 is 2. So one parentheses is going to have a positive 2, one's going to negative 2. If you're unsure, you can check that part with an area model. Sorry, I kind of ran out of room. And what will happen is you'll get this. These will cancel out, and you get a difference of 2 squares. So, difference of 2 squares are really easy to recognize. But you may have to take out a GCF. And again, don't forget to put the GCF in the front of the answer. Okay, these are called perfect square trinomials. When you factor them, they come out to be squared. If you don't recognize it, not a big deal. You can still factor it. You may not recognize that's a perfect square trinomial, and you may just go through an area model and say, okay, 36x squared adds to be 12x. I just think that if you see that, hey, 6 and 6 works, 36 is a perfect square. If I take the square root of 36, I get 6, and 6 plus 6 is 12. It may be a little bit faster of thinking of your factor pairs. Same parentheses on both. 2x and 2x on both. 2 goes into 6 3 times, and you get exactly the same thing in both parentheses. I don't know where I'm going to write the answer. I'll write it up here. 2x plus 3 squared. Or you can write it as 2x plus 3 times 2x plus 3. Just a little faster to write 2x plus 3 squared. Zoom in a little bit so you guys can see that a little bit better. Again, it's not wrong to write it as 2x plus 3 times 2x plus 3, but a little bit shorter, just write 2x plus 3 squared. Then you recognize it's a perfect square trinomial. Okay, so if I'm looking at the next one, 9's a perfect square, 25's a perfect square. Maybe it's a perfect square trinomial. Okay? and let me go back for a second. Perfect square trinomials have to have a positive for the last number. Have to be, because both things have to be the same sign. This one, they're both going to be a negative. And if you wanted to, you could do out this question. 9 times 25, okay, 225. And I got to get negative 30x. You may spend a lot of time, but split the 30 in half. 15 and 15. Does 15 times 15 give you 25? It does. So they are both negative, because a negative times a negative is a positive. So you get a perfect square trinomial. It just makes your guessing and your factor pairs easier. 3x, 3x, minus 5, minus 5. So we could write the answer as 3x minus 5 squared. Makes my life a little bit easier, a little bit shorter, not having to think so hard about factor pairs. Okay, this we'll get to more. These are the most missed questions on the test because people don't keep factoring completely. You're not going to see this on this homework except for number 19, which we will definitely go over on Monday. Okay? But I want you to recognize this is to the 4th power and that's to the 8th power. They look like difference of 2 squares. They both have 2 terms, a binomial. They both have subtraction. Are they difference of 2 squares? So this power just has to be even. Okay? So let's see. If we put x to the 4th here and negative y to the 4th here. Okay? If I recognize it's a difference of 2 squares, I might know the answer right away. So I have to get a negative x to the 4th, y to the 4th, and I have to get 0. So one has to be negative, one has to be positive. So maybe a negative x squared, or sorry, negative x squared y squared, that might be hard to think about. You probably know the square is. But if we do this, we might recognize that that's going to work. It's a difference of two squares. I just took the square root of each number. If you think about last chapter, the square root of x to the fourth, I can get two pairs of x's to come out. The square root of y to the fourth, I can get two pairs of y's to come out. So right now, I have x squared minus y squared, x squared plus y squared. Okay, hint, you might have to factor more than once. Do you recognize that one of these is still a difference of two squares? Yes, the first one is a difference of two squares. Subtraction, x squared, y squared. So I can write that first parentheses as x minus y, x plus y. The second one can't be plus. You leave it alone. Again, this will be a big emphasis as we go next week. And the only one that's like this on your homework is number 19. Okay, nothing else will be. Okay, last one. So I'm looking at this one. Hopefully you recognize there's a GCF. I'm going to take out a 2. That looks like a difference of two squares. Why? Because 9 is a perfect square. Again, I can take the square root of x to the 8th. Whoops, sorry. From last chapter, I can make 4 pairs if I take the square root of x to the 8th. So let's make sure I'm going to put x to the 8th here. I'm going to put a negative 9. Again, I took out the GCF. I'm going to split this to x to the 4th and x to the 4th because that works. I'm going to split this into negative 9, or negative 3 and positive 3. This would give me a negative 3x to the 4th. This would give me a positive 3x to the 4th, which cancels. So I'm left, which I'm going to put down here, x to the 4th minus 3, x to the 4th plus 3. Okay, before you circle your answer, I'm going to circle it so you can see what I wrote. You should always check if this is a difference of two squares. This is not, 3 is not a perfect square. So I cannot factor again. So this last part is a little challenge. Again, you don't have any questions on your homework like that today, but you will as we go farther in the chapter, except for number 19. Okay, so let's look at the worksheet one more time that we started on the block day. So you guys should have already, but it's not due till Monday, start on this. You should factor these. Okay, sorry, let me go down farther. You should factor these with an area model. Okay. As you get farther down, 7, 8, and 9 all have GCFs you can take out, except maybe not 9. I might be wrong. 9 doesn't have a GCF. But 7 and 8 have a GCF. We'll talk about those on Monday. Go to the back. (10, 11, and 12) all have GCFs. You should take out, make sure you put in the answer. Again, we'll talk about some of these on Monday. And you should be able to recognize that some of these are difference of two squares, and some of them might be perfect square trinomials. Okay, hopefully you recognize that the last two cannot be difference of two squares. Okay, perfect square trinomials. If you don't recognize it, you just do an area model and you'll be fine. Hopefully you recognize that you can take out a GCF on a couple. This one gets people and this one gets people. This is the one you have to factor a bunch. This one is very similar to what we just did on the last example, but it's x to the 4th instead of x to the 8th. But it's part of what we just did. pretty similar to it. Okay? So your assignment is to finish worksheet 2.4. We'll go over some of these on Monday, and then we will start on 2.5. Have a good weekend. I will see you guys on Monday. Bye.